Previously, when we looked at equilibrium problems, we were dealing with concentric forces. These are forces where their lines of action all cross through the center of mass. These forces cause zero torque, so there was no rotational motion. In that case, we applied the first condition of equilibrium. The first condition of equilibrium is Newton's first law. It says for an object that is not accelerating, not linearly accelerating, so it's either at rest or moving at a constant velocity, then the net force acting on the object is equal to zero. This means that the net force in both of the x and the y directions acting on the object must also be equal to zero. Now that we're considering rotational motion, in order to ensure that the object is not rotating, when we have forces that are non-concentric, meaning that their lines of action act at different points of the rigid body, then we need to apply the second condition of equilibrium as well. The second condition of equilibrium says that the net torque acting on the object is also equal to zero. This ensures that there's no angular acceleration of the object, so the object is in equilibrium. Torque can be calculated using one of the three methods that I explained in the previous section. Now, since this object is in equilibrium, it can't have a net torque around any axis of rotation. So this means that we can choose the pivot point or the axis of rotation and sum the torques about that point. Often this can be done strategically to choose a point where there are unknown forces or more than one torque to simplify the problem, and I'll show you that in the examples. So when we have an object in equilibrium, now that we're considering rigid bodies, we need to account for both of the conditions of equilibrium. So the first condition, that the net force is equal to zero, and the second condition, that the net torque is equal to zero. Now, this actually means that there's no angular acceleration. For us, we're generally going to see problems where the object is at rest. This could also apply to an object that is rotating at a constant angular velocity. Example 5, a uniform beam of length L equals 3 meters is supported at its center and is subject to two forces as shown. For this problem, use an axis through the center. A. Calculate the torque due to F1 about an axis through the center. B. What is the torque due to Fg and Fn? C. If the object is in equilibrium, determine the magnitude of force F2. Alright, so let's start by finding the torque due to F1 about an axis here at the pivot point through the center. So the torque 1 will be R1 F1 sine theta 1, and then we can add the sine. This would rotate the object counterclockwise, so that's positive. And we have half of the length here since the pivot's in the center, so that's 1.5 meters times 20 newtons, sine 45, the angle between R and F, which gives a torque of 21.2 Newton meters. Part B asks for the torque exerted by Fg and Fn. Both Fg and Fn are here at the center of the beam because the pivot is here, so that's where the normal force is exerted, and the weight is at the geometric center of the object. And since that's where our axis is, R is 0, and each of these forces exerts 0 torque. So the torque due to Fn is 0, and the torque due to Fg is equal to 0. Okay, now we're told that the object is in equilibrium and asked to find the value of F2, which is at 1/4 L from this end of the beam. So let's use the second condition of equilibrium, which says that the sum of the torques acting on the object is equal to 0 since it's not rotating. So since these torques are 0, we'll have the torque due to force 1 plus the torque due to force 2 equal to 0. And those are vectors, so we'll have torque 1 equal to negative torque 2. Or we could write that the other way, that the torque due to F2 equals negative of torque 1, since that's the value that we have. So that will be negative 21.2 Newton meters. And now writing the relationship for that torque, torque 2, going back to the diagram, it would pull the object this way, which is clockwise, so that's a negative torque. So we have negative R2 F2 sine theta 2. And now we can solve. So we have F2 equals negative torque 2 over R2 sine theta 2. So that's going to equal a negative of a negative, so 21.2 Newton meters positive over R2, which is 0.75 meters. This is the distance from the pivot to F2, this distance here, which is also a quarter of the length. And then sine of 90, since this force is also perpendicular to the beam. And that gives 28.3 newtons for the force for the magnitude of F2. Example 6, a 50 kilogram seesaw has a length of 5 meters. It sits atop a triangular support that lies below its center. A 30 kilogram girl sits at the far end of the seesaw. Her 80 kilogram father sits on the other side at a point that keeps the seesaw in balance. A, what is the normal force exerted by the support? B, where is the father situated? Answer with the axis of rotation, 1 at the position of the girl and 2 at the support. Okay, so let's begin with a free body diagram for the seesaw. The daughter sits at one end, so this is her weight, and then the father will be on the other side, a distance in from the center. Since he has a higher weight, he'll have to be closer to the pivot point in order to balance the torque of the daughter. And then at the pivot point, we have the normal force of the support and the weight of the beam. So the first question is, what is the normal force exerted by the support? Let's use the first condition of equilibrium, that the net force, specifically in the y direction for this problem, is equal to 0. So we have Fn minus the force of the father minus the weight of the beam minus the weight of the daughter equals 0. So the normal force will equal the force of the father plus the weight plus the force of the daughter. So that's the mass of the father times g plus the mass of the seesaw times g plus the mass of the daughter times g. And I'll just collect all of those masses and multiply by g. So we have, that up a bit, 80 kilograms plus 50 kilograms plus 30 kilograms times 9.8 newtons per kilogram, or meters per second squared, and that gives 1,568 newtons for the normal force exerted by the support. All right, in part B, we're going to use the second condition of equilibrium to find where the father is positioned. So I'll call this RF from the pivot point. And we're asked to do that two ways. First, using the axis of rotation as the position of the girl. So this is different than we did in the previous problem. So we're going to use our axis of rotation here at the daughter. So in that case, the torque due to the daughter is equal to 0, but the torque due to the normal force and the weight will actually be non-zero if we imagine this as our axis of rotation. So let's do that. So the torque due to the daughter is equal to 0. So the sum of our torques equals 0, which means that we'll have the torque due to Fn plus the torque due to the weight plus the torque of the father all add to 0. Now let's look at the diagram again. Each of these forces is at an angle of theta of 90 degrees. They're all perpendicular to the beam. Then if we're imagining this is our axis of rotation, the normal force will rotate the object clockwise, so that will have a negative torque, whereas the forces of the father and the weight of the beam will rotate the beam counterclockwise, which will be positive. So we can include that in our second condition for equilibrium line. Okay, so I'll have first, starting with the torque due to the normal force, this was negative L over 2, since it's at halfway through the beam, halfway down the beam, negative L over 2, and then we have the force, the normal force, and then plus L over 2 times the weight for torque due to Fg, and the torque due to the father will be plus Rf, the unknown, times the force of the father, which all add to 0. All right, so let's solve for Rf. This gives me Rf equals L over 2 Fn minus L over 2 Fg over the force of the father. So L over 2 is 2.5 meters times 1,568 newtons minus 2.5 meters, I have times 50 kilograms times 9.8. Ran out of room for that there, so times G to get the weight. And then all of that is divided by the force of the father, which is his mass, 80 kilograms, times 9.8 newtons per kilogram. And then calculating that gives us a result of 3.44 meters from the end of the beam, or from the location of the girl. Now if we look at the diagram, that looks about right, since the beam is 5 meters, so this is 2.5, and then it could be about 3.44 meters to where the father is located. All right, now let's solve part B again, using instead the axis of rotation here, which is kind of the obvious choice, through the center support. This choice is nice because the torque due to the normal force is equal to 0, since it's now at the axis of rotation, and the torque due to the weight is equal to 0. So that will simplify our mass slightly. And when an object's in equilibrium, since it's not rotating about any point, we can choose the axis of rotation. Okay, so then the sum of our torques, second condition of equilibrium, are equal to 0. And that means that the torque due to the daughter plus the torque due to the father must sum to 0. And we can see they're opposite in direction. So the daughter would cause a clockwise torque and the father would cause a counterclockwise torque. So we're going to have negative R, the distance to the daughter, which is L over 2 as well. You could put that if you wanted. The force of the daughter plus R, the distance to the father, which is our unknown, times the force of the father, equal to 0. And then solving for the unknown gives Rf equals Rd Fd over Ff. So L over 2, 2.5 meters, times the mass of the daughter, 30 kilograms, times G, just plugging in mg for her weight, over 80 kilograms times 9.8 newtons per kilogram. And this gives me 0.9375 meters, and this is to the left of the support. And so let's recall that previously we had 3.44 meters from the daughter, so let's just double check. The one answer we received was this, 3.44 meters from the location of the daughter, and this time we found that this distance was 0.9375 meters, and you can check if you do 3.44 minus 2.5, we do get this value. So both methods gave us the same distance or the same location of the father on the opposite side of the beam. Example 7, a 30 kilogram, 10 meter long ladder leans against a frictionless wall at an angle of 50 degrees from the horizontal. What is the minimum value of the coefficient of static friction between the floor and the ladder that would prevent the ladder from slipping? Often in the torque section you will come across ladder problems. This is a good example of a uniform beam where forces are acting at different locations. So let's start with the free body diagram. The normal force will be exerted in two places, or there are two normal forces. One at the wall, here I've called that Fn2 since the ladder is in contact with the wall, and then again on the floor, that's Fn1, the normal force between the ladder and the floor. Then the weight of the ladder acts at its midpoint, and we know that this wall is frictionless, but there's friction between the ladder and the floor. So the ladder will attempt to slip outwards, so static friction must oppose that motion and be directed inwards towards the wall. You can also tell that the force of static friction has to be directed towards the wall because the net force has to be 0 in the x direction, and the only other horizontal force is directed to the left or away from the wall, this normal force from the wall. Okay. And we have 50 degrees for our angle between the ladder and the floor. So ultimately we want to find the minimum value of the coefficient of friction, which will happen when the force of static friction is at its maximum for that coefficient between the ladder and the floor. And this is the relationship for the maximum value of static friction. It equals mu s Fn. Make sure you use the normal force to the floor since that's where the friction is acting. So to do this, we're going to need to find that normal force. So let's start by applying the first condition of equilibrium. So the sum of all the y forces equals 0. So in the y direction, we have Fn1, which is upwards, minus Fg equals 0. So we know that Fn1 equals Fg, which is mg. So 30 kilograms times 9.8 newtons per kilogram, which is 294 newtons. Okay, and let's apply the same condition to the x direction. The net force in the x direction equals 0. So we have the force of static friction minus the normal force on the wall equals 0. So this tells us that the normal force on the wall is equal to that force of static friction, and we'll use that relationship later. So now what we'll do is use the second condition of equilibrium to find this force, which will give us static friction, and then we can apply this relationship up here in order to find the coefficient. So since I have two forces at the base of the ladder, I'm going to use this as the pivot point, since it will simplify the problem by making the torques due to Fn1 and Fs 0 and allowing us to solve for that normal force. Notice if we look at the signs, the weight is going to pull that ladder clockwise, so negative, and then the normal force would pull it counterclockwise if it was to rotate the ladder, and that's a positive torque. Okay, so the second condition of equilibrium, the sum of all the torques are equal to 0, which means the torque due to Fg plus the torque due to the second normal force are equal to 0. So we have negative L over 2, the weight acts halfway up the ladder, Fg, sine, the angle here, going back to the diagram, is this angle between R and F. R is along this line. So we want this angle in here. If we extend Fg down, which is vertical, this is a right angle triangle. So this angle in here would be 180 minus 50 minus 90, which is 40 degrees. So it's sine of 40 for that torque. plus L, since the normal force acts at the end of the ladder, we have L, Fn2, and this torque was positive, sine of 50. And again, I'll just show you why that angle is sine of 50 when I go back up to my diagram. So this angle is in here is 50, which means that we also have 50 degrees here. This angle would be 40, and then 90 minus 40 gives 50. So that's sine of 50 between Fn2 and R. Okay, and then notice L can cancel, which is a nice reason for using L in the equation. And then we can solve for unknown, which is Fn2. So I get Fn2 equals 1/2 Fg sine 40 divided by sine 50. So 1/2, 294 newtons, sine 40 over sine 50, which gives a normal force of 123.3 newtons. And as explained previously, we know that that is equal to Fs, and that's going to be the maximum value of static friction here. So that's because we want that to be the maximum in order to find the minimum coefficient that can produce that force of static friction. So Fs max equals mu s Fn1. So we'll have mu s equals Fs max over Fn1. 123.3 newtons divided by 294 newtons, which gives a coefficient of 0.42 between the ladder and the floor. Example 8, a hungry 800 Newton bear walks out on a beam in an attempt to retrieve some goodies hanging at the end. The beam is uniform, weighs 250 newtons, and is 6 meters long. The goodies weigh 75 newtons. Angle theta equals 60 degrees. A, when the bear is at x equals 1 meter, find the tension in the wire and the components of the reaction force at the hinge. B, if the wire can withstand a maximum tension of 900 newtons, what is the maximum distance the bear can walk before the wire breaks? All right, so looking at this, we're asked to find 3 unknown forces for part A, the tension in the wire, and the reaction force, the components of it in the hinge. So first I've drawn a free body diagram with the locations labeled again. So I have the weight of the bear at a distance x, which is 1 meter from the hinge. The weight of the beam, which is 250 newtons in the center of the beam, and then the weight of the goodies at the end of the beam. The tension in the string is here at an angle of 60 degrees, and then we have 2 components of the force at the hinge. So the y component of the force will hold this up. We have all 3 weights here that are supported by the hinge and the tension. And then this horizontal force from the hinge, we can see that it has to be outwards from the wall since this x component of the tension is to the left and it's the only other force in that horizontal direction. So with 3 unknown forces, we're not going to be able to solve for the unknowns using just the first condition of equilibrium. Let's start with the second condition, which is torque, and use this hinge as our pivot point, which makes the torque due to the hinge force, the y and the x component, both equal to 0, and then we'll have only one unknown, which will be the tension in the string. So we have the torque due to the hinge force, both y and x components, equal to 0, and the net torque overall is equal to 0. Again, this is the second condition of equilibrium. And let's sum the torques about this point. So I'm going to have this torque due to the tension, which would be a counterclockwise torque. So the torque due to Ft plus these 3 weights, which are all clockwise. I'll add the sign in the next step. So the torque due to the bear and the weight and the goodies. all add to 0. All right, so let's fill in the expression for each torque. This tension is at a distance L from the pivot point, so we'll have L Ft sine 60. Again, that was the positive torque. Now these three are negative, so negative, this is at a distance x from the end, so x FGB sine 90. I won't write that in. We have sine 90 just to simplify the expression because we know sine of 90 equals 1. So sine 90 here, and then I'll have minus. This weight is at a distance of L over 2 from the end, so L over 2 Fg, again sine 90, and then minus the force of the goodies, which is at a distance of L at the very end of the beam, and again sine 90 since all of these forces are perpendicular. So sine 90 here, if you wanted to write it, it is equal to 1. Okay, and then now we can solve for the unknown, which is this tension force. So I end up with Ft equals, we'll have x times Fgb plus L over 2 times Fg plus the force of the goodies times L all over L sine 60. And then we can plug in numbers to find the tension. So 1 meter times 800 newtons plus 250 newtons times 3 meters plus 75 newtons times 6 meters. And that's all over the length, 6 meters sine 60. And take a minute to calculate that, and that gives me 385 newtons for the tension in the cord. Okay, now let's use the first condition of equilibrium to find the reaction forces in the hinge. So in the x direction, our net force in the x direction equals 0. So I'm going to have the only two x forces equal to 0. Looking again at our diagram, this is just FHX and the x component of the tension. So this means that the hinge force is equal to FTX, which will be Ft cos 60. So this is 385 newtons cos 60, which is 192.5 newtons. That's the x component of the reaction force in the hinge. And now the y direction, sum of all the y forces equals 0. In the y direction, I have FHY, which is up, plus FTY, which is also up, minus the weight of the bear, the beam, and minus the weight of the goodies. And all of that has to equal 0. So I'll have the hinge force in the y direction equals negative FTY plus the weight of the bear plus the weight of the beam plus the weight of the goodies. So that's going to be negative 385 sine 60 plus 800 newtons plus 250 newtons plus 75 newtons. Okay, I just made a little bit more space. So adding those all up to get the y component of the hinge force, it's 791.6 newtons. So our three unknown forces were Ft equals 385 newtons. And then we have the x component of the hinge force, 192.5 newtons, and the y component of the hinge force is 791.6 newtons. All right, now in part B, we're asked, what if this tension has a maximum value of 900 newtons? How far could the bear walk out on the beam? So what is this value of x? That's our unknown now if the tension is at its maximum value of 900 newtons. Since we're looking for a location that only shows up in the sum of the torques equation, the second condition, let's start with that. So the net torque is equal to 0. And again, using this as our pivot means that we don't have torque exerted from the hinge forces. They both have 0 torque. So we have the torque due to the bear plus the torque due to the weight Fg plus the torque due to the goodies plus the torque due to the tension equal to 0. All right, so the torque due to the bear is negative Fg of the bear times x, negative because it's clockwise again, same as in the last part, and then minus L over 2 Fg. These are both perpendicular, so we have sine of 90, which is equal to 1, minus L, since it's at the end here, a distance of L from the pivot, times Fg of the goodies. And then we have our positive tension torque, the same as in part A again, so plus L Ft sine 60 equals 0. And this time the unknown that we're solving for is x. So I get x equals negative Fg L over 2 minus Fg of the goodies times L plus the tension L sine 60 over Fg of the bear. All right, and now we can plug in numbers. Negative 250 newtons times 3 meters minus 75 newtons times 6 meters plus this maximum tension 900 newtons times 6 meters sine 60 over 800 newtons. Okay, and this gives a distance of 4.35 meters. The length was 6 meters of the beam, so the bear can walk out to a distance of 4.35 meters if the tension goes up to its maximum value of 900 newtons. Any further than that, and then the beam would start to rotate.